There is a blue, shimmering, jewel-like planet called Earth. Earth is the third planet from the Sun. When men first looked back at Earth on their way to the Moon, they realized how fragile and small our world appears in the vastness of space. Clearly, the study of Earth and its thin protective atmosphere is important for us to pursue. Now let's go to a NASA film called Earth, Space, Our Environment to learn how the Sun's emissions affect Earth.
Weather and climatic changes, atmospheric pollution and disturbances of the ozone layer, worldwide magnetic storms that disrupt radar and radio, telephone communications, and even cause power failures. All these may well be controlled by eruptions on the Sun, which affect Earth's magnetism and create the auroras by means of a vast engine around the Earth, the magnetosphere. Because this magnetosphere can affect Earth in so many ways, understanding how it works might help us cope with climate and pollution variations, and even help us in planning the use of our food and energy resources. But how can we start to understand the magnetosphere? In 1600, William Gilbert told us the Earth was a great magnet extending into space. 10 years later, Galileo Galilei turned his telescope on the Sun and recorded how its surface constantly changed. But then for 300 years, the Sun and Earth pursued their courses, and no convincing theory was able to connect Galileo's solar changes with Gilbert's terrestrial magnetism. Until a solar theory in 1890 suggested that the Sun throws out particles which travel to the Earth to be caught by its magnetism. In the 1950s, the Sun's own magnetism, it was suggested, flowed into space to envelop the Earth and generate the auroras high in the terrestrial sky. Yet this was only speculation on how the Sun might affect the Earth through an invisible magnetosphere. Only by actually getting measurements in space could the true facts be unearthed. In the late 20s, Goddard, the American, built the first practical rocket craft. The Russian Sputnik was the first space success.
2, 1, 0.
The American Explorer soon followed, carrying with it a Geiger counter. The signals produced by the counter enabled Dr. James Van Allen to confirm that he was recording something real but unexpected in space.
It repeatedly did the same thing in the same general range of altitude and latitude and longitude, and therefore it must be a true physical effect that we were observing.
This was the first discovery in space. The Van Allen radiation belts, particles invisible to the eye, which came perhaps from the Sun, were trapped in the space around the Earth by the planet's magnetism. This was the first step in establishing a link between the Sun and Earth through the magnetosphere.
And when the radiation belts were discovered, I was very keen on the idea that the fast particles from the Sun would be able to fill these radiation belts, and that the stored particles we were seeing there were in part, or perhaps in major part, coming from the Sun. And so the paper in which the word magnetosphere was coined was that there would be a region around the Earth where the Earth's magnetic field dominated the circumstances.
The first concept of the magnetosphere was that of a region where Earth held particles that were captured from the sun. But did these particles really come from the sun? To find out, instruments had to be fired further out into space to really discover if the erupting surface of the sun did throw out particles and magnetism all the way to the Earth. And from space, this answer came back. Streams of particles flowed from the sun, dragging out the sun's magnetism, a solar wind rushing into space. But Earth's magnetism in the magnetosphere deflected the solar wind around the Earth. So how then could the solar particles get in and be caught? Solving this space problem could be difficult.
You're going to have them penetrate to the atmosphere. And so one of the exciting things that have been done in the last few years was find that if we went clear above the Earth's poles, that plasma from the sun would directly come down into the atmosphere.
This was the breakthrough. Solar particles detected entering directly into the magnetosphere. While within the magnetosphere, further measurement showed what was also invisible to the eye. Seas of plasma particles around the Earth, and huge particle streams moving thousands of miles back from the tail, perhaps to directly ignite the brightest auroras. But what could drive the magnetosphere into these vast movements? Could the solar wind rushing past outside the magnetosphere supply the energy?
Well, if I knew the answer to the question of how energy was transferred from the solar wind to the magnetosphere, I wouldn't be sitting in front of this camera talking about it. I'd be in my office writing as hard and as fast as I could to demonstrate what I believe to the colleagues which are also investigating this problem. It is contentious.
One theory hinges on a magnetic connection. Magnetism from the sun connecting with and dragging back Earth's magnetism. This would work like a dynamo in space, transferring energy into the magnetosphere, where it is stored until suddenly released in a magnetic storm to disturb the Earth and create auroras. For such auroras appear to be created when stored energy is released in a violent eruption throughout the magnetosphere. But where can proof of this be found? One place is the Arctic, where auroras are seen almost every night. And scientists search for clues to show how the magnetosphere collects energy from the sun, stores it, and suddenly releases it to the Earth, creating auroras in a burst of energy equal to that of a large earthquake. So analysis today concentrates on finding how the magnetosphere works and, in particular, what triggers its energy releases. Could it be changes in the solar wind?
The solar wind does not flow steadily and regularly. It carries perturbations, shock waves. Even the magnetic field changes in direction and intensity. When this happens, an instability is triggered in which suddenly an explosion occurs in the tail, in which magnetic energy that has been accumulated during a certain time is suddenly converted into particle energy. And that typical solar wind particle that had been trapped in the tail now suddenly is accelerated toward the Earth.
So, changes on the sun, which change the solar wind, appear to trigger an energy-filled magnetosphere into a sudden spasm, creating a magnetic storm, the brightest auroras, and affecting the whole Earth environment.
But there are still many of the apparent effects of the aurora borealis and the magnetic storms that defy detailed explanation. So there's a great deal more to be learned in the ionosphere and in the upper atmosphere of the Earth.
So investigations continue. This is a computer simulation of the Earth and auroras from space, part of an experiment to measure exactly how magnetosphere energy creates them. And beyond this, there are active experiments.
You really want to try to actively perturb the magnetosphere, the ionosphere, and the atmospheric system in controlled ways so that you're actually doing a laboratory experiment. You know what the input is, and you can measure the response of the system. And when we get to that point, we'll be able to really probe the specific processes which couple these regions together.
In Canada, there is an active experiment underway in which radio signals, which disturb the magnetosphere, are received from the opposite hemisphere of the world, the Antarctic. The signals injected here arc through the magnetosphere to give a record of the changes that are happening there. The most active experiments will be done with man in space, on the space shuttle.
With the space shuttle, we get the opportunity to put man into the experiments. Given the new capability that the shuttle will have, we'll be able to conduct a brand new variety of experiments that we've never had the capability to do before. And the scientist will be able to interact with the medium surrounding the vehicle, will be able to probe the medium, perturb the medium, and measure the responses. And that's really the way you understand things.
So what is understood of Earth space today? Laboratory simulations of a magnetic Earth and the solar wind streaming at it have been able to produce a visible representation of the magnetosphere. But the picture is blurred and out of scale. Only space measurements are valid in constructing a true diagram of the magnetosphere and its movements. Simplified images of this complex engine in Earth space, where until recently there was thought to be only empty stillness. This is, however, a gauge of our present-day understanding and ability to predict how changes on the sun will, in some ways, affect the magnetosphere and Earth environment. So today, at forecast centers like this, the sun is kept under watch around the clock.
Activity in region 331.
What kind of activity you have?
The filament in 331 is active. It is shifting off bands to the red. Flare. Beginning in 331. Start time 1958. Location North 13, East 28.
Dad, I've got a big flare. Could you give me some help?
Today, we know that the magnetosphere is a complex engine through which the sun causes enormous disturbances to the Earth's environment.
FAA, this is the Forecast Center in Boulder. I'd like to report a major solar flare in progress.
When we learn all the details of how the magnetosphere works, we will be able to predict its effects on the atmosphere and its influence on short and long-term weather patterns and on changes in the Earth's ozone layer. Then we would know what changes to expect in our environment when we see the sun shaken by a huge eruption. All this lies in the future, but many think the groundwork is now being laid.
Ecology, the balance of nature, is important to all life. One of the tools we can use to monitor this balance of nature on Earth is the satellite. Satellites can be used to observe our planet from a high vantage point. A NASA film called Remote Possibilities tells the story.
From far out in space, the Earth appears serene and beautiful, displaying no hint of our crowded planet's many problems. As we have used and changed our planet, we have become aware that in many ways we are exhausting it. Exhausting our food supplies, our sources of energy, our natural lands, exhausting the potential of even the once seemingly limitless oceans. Management of Earth resources is at a critical stage. It has never been more important that we understand the environmental relationships of our planet. Scientists are striving to apply the technology of the space age, the quest for more and better information about these complex relationships. In 1972, a new kind of satellite left the launch pad and rose to an altitude of 910 kilometers from Earth. There it settled in a circular orbit around the planet. This satellite, called Landsat, opened a new era of Earth resource management. Landsat's recordings of the Earth's surface are not photographs as we usually think of them. They are images. Images formed using the techniques of remote sensing, that is, sensing from a distance. We're all familiar with remote sensing. You're using a remote sensor to view this film. Landsat uses another kind of sensor, an oscillating mirror, which captures the light reflected from the Earth's surface. Different areas of the Earth's surface reflect varying amounts of light. The oscillating mirror of Landsat's multispectral scanner directs light reflected from the surface of the Earth to 4 sets of sensors inside the satellite. Each of these 4 sets of sensors is sensitive to a different wavelength of light. Light as perceived by our eyes is only a part of the electromagnetic spectrum. Other parts of this spectrum include ultraviolet light and infrared light. Landsat is sensitive to the red and green bands of light in the visible spectrum and to 2 infrared bands. These are the wavelengths of light, called spectral bands, which are used to create Landsat's unique images. An astronaut can bring back film when he returns to Earth, but Landsat, which will orbit for years, cannot. Instead, it transmits signals which are used to form images. Landsat's oscillating mirror scans the ground and receives light from small areas called picture elements, or pixels. Each pixel is 1.1 acres, approximately the size shown here. Landsat receives the light reflected by a pixel. Sensors inside the satellite give the light a number between 0 and 63. Bright areas receive high numbers. Areas with less reflectance receive lower numbers. Each area of the Earth is seen as a pattern of lights and darks, coded with numerical values in each spectral band. Landsat sends these numbers to receiving stations on Earth, where technicians record them for future use.
5304.
Transmitter drive is on. 2A, go for command.
135524. Victory off at 135952.
Link 4 signal strength, -113.
The numerical information is received and stored on tape, which can then be used to make images on film. There are over 7 million pixels in a Landsat image. The amount of light each pixel reflects is recorded as a numerical value. These numbers, one for each pixel, are now converted to the blacks, whites, and grays of a Landsat image. This process happens simultaneously in each of the 4 spectral bands, producing 4 black and white images of the same scene. At any given point in an image, the reflectance value is different in each of the 4 spectral bands. For example, the outlined area, a redwood forest, might vary in reflectance from 15 to 35. By combining these separate black and white images and printing them through color filters, the differences in them can be used to emphasize specific Earth features. The colors, however, are not normal. Vegetation, for example, is seen as red. For many uses, these photographic products of Landsat data are a great advancement over any other form of aerial surveillance.
The photographic product is a very useful tool, but it does have one disadvantage. It does not allow us to display and analyze each pixel, that is, each picture element. However, this can effectively be done with a digital computer. We can use the cursor or the light square there in order to train the computer on a particular theme that we want to analyze. In this case, it's the sediment emptying out into the ocean from a river. We can now display all similar areas of sedimentation in the image in a particular color. In this way, we can display the numerous themes which exist in the imagery on the digital computer.
Landsat views offer researchers one totally new service. The satellite orbits the Earth in such a way that it always passes over the same area at the same time of day, recording exactly the same spot on Earth once every 18 days. This repetitive coverage provides an ideal tool for monitoring changes on the Earth. For example, note how well these images of the Washington, D.C. area show seasonal changes. The bright reds indicate the healthy vegetation of spring and summer. The edge of a snowfall is clearly defined on the winter image. Landsat images contain a wealth of detailed information, some of it obvious, but much of it very subtle. These images provide raw material to be studied and interpreted by people engaged in many kinds of research.
I've been working with managers of the Great Dismal Swamp to make a plant association map of this 125,000 acre area. The managers of the Great Dismal Swamp are very interested in finding a method that is reliable to make these maps because the area to be mapped is so difficult to walk around in. Not only difficult to walk around in, but difficult because of all the bugs and standing water. The importance of monitoring the Great Dismal Swamp is to preserve one of the eastern seaboard's last remaining wildlands. When we began mapping the Dismal Swamp, certain features were easily located. Lake Drummond in the center of the swamp stood out clearly. Cleared areas show up distinctly. This area was cleared by a lightning fire. One area on the computer scene puzzled us. It showed up as evergreens, but different from the evergreens which we had previously mapped. We checked it out with a trip to the swamp. We discovered that Landsat had identified a beautiful cedar forest. The final product of our research was a thematic map of the Dismal Swamp showing plant associations. In the future, we will be able to compare new Landsat images to this base map in order to monitor changes that take place in the swamp.
Landsat's imagery is available for use by anyone in any nation. The Eros Data Center in Sioux Falls, South Dakota distribute images and tapes to people all over the world. Landsat's images are providing new sources of information about many different kinds of Earth resources. The satellite is being used to map the extent of flood damage. Landsat's before and after images make excellent maps to study how fast water recedes and damaged land recovers. Landsat is keeping track of land development. For example, how well areas damaged by strip mining are being reclaimed. Scientists are using Landsat to map remote areas as possible wildlife habitats. To search the Earth's surface for clues to new mineral deposits. To inventory the world's agricultural crops so that food and fiber resources can be better managed. Future geography books will use Landsat images to show the world as it really is. This map, made of 569 separate Landsat images carefully pieced together, gives a dramatic view of the United States never before available. Perhaps it is Landsat's beautiful views of the Earth which remind us most of all that the Earth is a treasure.
Other satellites in orbit some 22,000 miles above Earth provide important views of weather. Daily forecasting of weather is more accurate than in the past because satellites are able to see the formation of storms and other weather conditions at remote parts of the Earth. The storms can then be tracked to the more populated regions. 12 American astronauts walked on the moon looking for clues about the origin of the solar system, perhaps preserved there. But first, we had to photograph the moon from close range and land probes to see if it was safe for men to land. During our next program, assignment Shoot for the Moon, we will see how the moon was studied before men went there. This is Larry Ross saying goodbye from NASA's Lewis Research Center in Cleveland, Ohio.